This worksheet starts off by having us design some custom polynomials to see if we understand the connection between the factors of the polynomial and the zeros of the function. So in this case, the first case, we want zeros at x equals 1 and x equals minus 1. So a function that will do that is just one where we have factors, where the first factor is 0 when x equals 1, and the second factor is 0 when x equals minus 1. So this function will accomplish what I want. It will have degree 2. I can tell that when I multiply these two terms together, it's multiplying the x term here times the x term here, that'll be my highest degree term, will be x squared, because I don't have to multiply it out to see that. That's the correct answer. In the second problem, we have a little more flexibility, because I can accomplish having zeros at x equals 1 and x equals 0 without having to have a degree 3 polynomial. I could just do this, again, because this term is 0 when x is 0, and this term is 0 when x is 1. So if you plug 1 in for x, you're going to get 0. If you plug 0 in for x, you're going to get 0. But this doesn't have the desired degree. We want something that has degree 3. So, and if I multiply this out, it'll only have degree 2. So that means that I can add multiplicity. I can add one of these factors more than once. So to do that with writing a factor, I could just tack another x minus 1 on there. That now makes me have a degree 3 polynomial, and I still only have zeros at x equals 0 and x equals 1. We typically don't write it that way. We typically write it as x times x minus 1 squared. But another perfectly good answer would have been g of x equals x squared times x minus 1. So what we're doing here is making one of the factors have multiplicity 2. That'll raise the degree of the overall polynomial, but it still only has zeros at 1 and 0. In the next problem, there are 4 factors there, and I want it to have degree 4, so I'm going to be able to do this just with linear factors. This is a case where I can just do it by rote, but I'll have these fractions running around in the problem. So I can show you a way to not have fractions if you don't like them. So again, all I've done is made sure I have one factor for each 0. So when x is 0, this guy will be 0. When x is 1, this will be 0. When x is 2/3, this term will be 0. And when x is negative 3, this term will be 0. So the product of these terms will be 0 at exactly the numbers 0, 1, 2/3, and negative 3. And you can see that it will have degree 4. If I pay only attention to the highest degree term, I'll have an x times an x times an x times an x, which will be an x to the 4th. So this will do just fine. And it does have the condition that I want, having a lead coefficient of 1. If you did multiply this out, it would be x to the 4th plus blah, 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 blah stuff. If you don't care about that, if you don't care about this condition, it's a little bit nicer to look at a polynomial where you keep your values whole numbers. And the way I can do that is by thinking about a different factor here. All I need here is for this factor to be 0 when x is 2/3. So I could accomplish that by using a factor of 3x minus 2. If you think about it, when x is 2/3, this factor is going to be 0. So that will also work. Either answer is okay. Technically, this is the right answer because it does have a lead coefficient of 1, as we wished. But that's sort of a fake condition. That's a condition that's just there so that we all get the same answer. But in a lot of these problems, there's more than one answer. The second 3 problems on the first page add multiplicity, and so that's telling you more what to do. It's less open-ended, so that's actually easier. If there's a 0 at x equals 1, that means that x minus 1 is a factor, because when x is 1, this factor will be 0, and I'm told it has multiplicity 2. So I'm going to put a square on there. I want a 0 at x equals negative 2, so that means I need a factor of x plus 2, because when you put negative 2 in for x, it's going to make that 0, and I want multiplicity 3, so I just slap a 3 on there. And so again, this will be a degree 5 polynomial, and we know from the even-odd business that there's going to be an intercept at 1, 0 where the graph just touches, and there's going to be an x-intercept at negative 2, 0, that the graph is going to pass through the x-axis. The question doesn't ask that, but that's the sort of analysis we have to do in other problems. So I'm going to skip on to the next. Once we have a factored form, it's pretty easy to analyze it. Again, to find the highest degree term from a factored form, I can just ignore everything but the highest degree terms. So leave the 2 there. Instead of x minus 1 squared, I just make it x squared. Instead of x plus 3 squared, make it cubed, make it x cubed. So in other words, in each factor, I'm just keeping the x term. And if I multiply those out, that's 2x to the 5th. So that's the highest degree term. The y-intercept is always just 0, comma, whatever you get when you plug 0 in. So I've got to calculate f of 0. But I don't have to multiply this thing out to do that. I can just put 0 in for x. It'll be 2. 0 minus 1 is negative 1 squared. 0 plus 3 is 3 cubed. So I have 2 times 1 times 27. So that means 0.54 is my y-intercept. So it's way up there. The x-intercepts are going to be places where the equation is equal to 0. So I just set my function definition, because remember again, the definition here, this equation, this expression is describing y-coordinates. So we want the x-intercept, we want to know where the y-coordinate is equal to 0. So we're trying to solve that equation, but the thing's already factored. So the only way that's equal to 0 is if x minus 1 is 0, or x plus 3 is 0. And so that means my x-intercept is going to be at 1, 0, that's going to be one of them. And at negative 3, 0, it's going to be the other one. And because the multiplicity at 1, 0 is 2, I'm just going to get a touch of the axis at 1, 0. And because the multiplicity of the other factor is 3, that's an odd number, the graph's going to pass through the x-axis at the x-intercept negative 3, 0. This last question, for each function above, find an approximation near the x-intercept. This is more of an advanced question. It doesn't come up too often, but when you take calculus, you are interested in this idea of approximating a function near another point. So I included those questions on here just so that you're used to the type of question. The method here is not something that really generalizes to calculus, but it's not too hard either. So let's just, let me just get my, I'll do the problem for the first one there. It says to use the smallest 0. That's just so that we're all using the same thing. So, so in the case of number 1, the smallest 0 is that one. Negative 3 is the smallest 0. So that's the leftmost x-intercept. So let me just rewrite the problem down here. So the function was f of x equals 2 times x minus 1 squared times x plus 3 cubed. And I want to know what's going on near x equals minus 3. That's my smaller of the two zeros. So the theory says that we can find this by just in this expression, in the factored expression, just replace everything in here with negative 3 except for in this term. So in other words, leave that term as it is, the term that that corresponds to the factor whose 0 is negative 3. We make x equals negative 3 everywhere else. So I'll have 2 times negative 3 minus 1 squared. And again, I leave this thing I double underline, just leave that alone. So there's going to be one factor that corresponds to that 0, and that's what you leave alone. You put the number in for everything else. So the thing in parentheses here is 4 squared, which is 16. So this is 32 x plus 3 cubed. So in other words, this graph, if you only look near x equals negative 3, like between like negative 2.9, negative 3.1, then you won't be able to tell much difference between the graph of f and the graph of g. They look very similar. The reason for doing this is that this is a much easier function to work with. it has a lot less going on. So in each case, these approximations, the idea is that I can use an approximation near a point because it's easier to manipulate that algebra expression. Of course, the trade-off is that there's no correspondence between these two graphs if you have values of x that aren't near -3.